All right. So last time we were here, one of the things that we were talking about was black body radiation. And Amberly, what is that?
Whenever something is heated up, it'll eventually radiate light.
Yeah, right. Yeah, and remember, light is just Roy G. Biv. You have infrared and you have UV and you have a lot of light. Exactly. So, but Madison, a problem arose, and that if you plotted this light that the body emitted, they couldn't. What was the problem? They couldn't what? Yeah, in fact, what predicted UV is going to be huge? Everything's supposed to be going in the dark. Heat it up, it's going to emit UV light. It's going to get a sunburn. It was our classical laws, the laws that we had at the time. They called it classical physics or something. But so that it was a big problem. So what was the solution? What components solved the problem? Quantization of energy, right? And also the idea that not all molecules and everything had the same energy. It was kind of dispersed. There's this distribution, right? Okay. Now quantization of energy is a very odd thing. Here's an example of quantization of energy. Turn this back on. I think it's an example of quantization of energy. Well, not only me, but a lot of people. Here's magnesium, right? And I could have shined it up a little bit. I should have. Alice do that. Are you working today? So we'll get the magnesium nice and shiny, right? And then here's the same magnesium, but it's just pulverized, right? It lost its reflective abilities. I mean, it's black now. Instead of reflecting everything, it's absorbing everything. It's in that microscopic world, man, things change dramatically, and they change fast. And in this microscopic world, the set of laws you're supposed to use is called quantum mechanics. And in the microscopic world, this quantization of energy is really enhanced. You can really see it. Here's my baseball. I could toss it to, right? Toss it. You ready? I'm gonna toss it to Amberly, right? Right. So we're used to, what's the T word that this ball's following? There's a glass behind you that makes me nervous. What? Trajectory. Every single moment in time, it has a speed and a position. Go to the microscopic world, make it an electron. We have no bloody, I'm really serious. All the experiments, all the technology we have, femtosecond lasers, it doesn't matter. We have no idea how an electron gets from me to Amberly. We have no idea. All we know is when it left and when it arrived. Now, they can, with some really fancy detectors, you can kind of narrow down, that, it might be here, in this region. It passed through this region right here. Some probability. But then they have no idea, even less idea, how fast it's going then. Its energy. Or if they change the parameters to, maybe let's detect its energy. They have no idea where it is. So in quantum mechanics, it's not a baseball anymore. It's a wave. That it's pretty much everywhere all the time. But not even so. If you go into a swimming pool, and if you make standing waves, what's a standing wave? You had to pretty much be really bored in the swimming pool to make this, but it works, right? You have to, like some square thing. Go in the kiddie pool, This would definitely work in the kiddie pool, right? Don't go in nice and soft so you don't make any waves, and then just in a steady motion. In fact, it really needs to be. You really need to speed your hands up and slow them down to make it work. In other words, you're not moving your hands at a constant speed. They're going fastest in the middle. So it's called simpler harmonic motion, but that's really what you got to be doing. And then you just start making these waves. And these waves, you're going to notice peak, trough, and they stay that way. Right? And so waves can also be acting like that. So that means an electron, it's going to be impossible for it to be here. Think of a standing wave, because they're supposed to be wave. Impossible for it to be here, impossible for it to be here, but it's 10% chance here, 10% chance. That's what we're getting into. Some very odd situations. But it works. In all the experiments, everything that we have so far, you can't explain it without quantization of energy, without these impossible things happening. You want to get an MRI. You want to, I don't know, for some reason, right? I guess that'd be a sad reason, but you right? Energetically, these electrons have to be doing energetically impossible things for you to get that MRI image. For you to get the scanning tunneling microscopy. In biology, maybe you saw those black and white pictures of a bed bug or something, right? You ever see these? They're black and white, and they might say STM on the bottom, but scanning tunneling microscopy. Electrons have to do energetically impossible things to get that done. What does that mean? That means I'm tossing this ball to Amberly, right? You and I can see it the whole time. But if it's an electron, it's possible that this electron went through the roof and back down. Very low probability, but it could happen. It can do energetically impossible things. It can pass through Rob and go on through, right? There's all these different possibilities that it could happen with a different probability for each single one. So it's the best thing we have, and it works. I mean, down to the minutest detail, it really, really works. You can't describe why this shirt is orange without quantization of energy, with what's going on at the molecular level. Okay. So this guy Schrödinger comes along, and since waves is what works, he comes up with a wave equation. And so these electrons, these are functions for an electron, but they have no meaning. Usually you think of a function, ooh, a trajectory, right? It has some meaning. This has no meaning at all. There's no meaning to this. It's just a wave function for this electron. And now you can do different things to this wave function and get energy, get position, and all that kind of stuff. But you have to use an equation like Schrödinger's wave equation here to get out the energy. And this big psi thing, that's the wave function. Okay. So how do you come up with these wave functions? Right? Well, one way is you just guess. That's pretty much what they do nowadays, because it's way too complicated. You know what the experimental energies are. You just go in the lab and you measure these things, and then you just sit there and have the computer emulate, right? Plug in a wave function, do all the math. Does it give you the right energy? If it doesn't, well, go back, modify the equation, come back. They call it like simplex is one of them, but just keep modifying the wave function until it gets all the right energies. Then once you do that, oh, our wave function is really, really good. Then we can use it for position. We can use it to determine momentum. We can use it to determine what is the best conformation for this drug to interact with this DNA in this site. You can make the problem as complicated as you want. It's just more computational powers involved. Okay. So let's take a look here. Whoa, thank you. Now, what is all this stuff? How about this H, the bar? I'll call it H bar. What is that? What was H? Madison, what was H? Now, H is Planck's constant. H bar is Planck's constant divided by, somebody know? 2 pi. Planck divided by 2 pi is h bar. Okay. Now that funky symbol, I call it psi. I think it's spelled psi. Psi, that's our wave function. Okay, that's our wave function. M is, little m, probably, Sandy, is what? The mass of what? The electron, right? This isn't going to work for a baseball. And that's why there's got to be something wrong, I think, right? Because if this theory, yeah, if something works, it should work for everything. I've said this before, but is there one book that we can pull off the shelf that works for gravity, works for relativity, works for, gravity's a big problem, trajectories, works for light, electromagnetic spectrum? No, there isn't, right? You have to pull off a different book for every different, they don't correlate. Just like here. This does not correlate with baseballs. It won't work. So it has to be the mass of an electron. Exactly right. Not even the mass of a molecule. It's too massive. Okay? Mass of an electron. Okay. Molecule, yeah, it might work. I know we're getting in, because just where does quantum mechanics stop and classical mechanics start? You know, it's going to be way less than this. You know, that's a blurry area there. But we have good answers with baseballs. We have good answers with electrons. We just have to pull the right book off the shelf. Okay. So little m is the mass of electron. This v of x. Notice this wave function is in here several times, but v of x, that's the potential energy function. The potential energy function is really what messes everything up. It makes all these calculations extremely complicated. And because it's describing what's the potential energy of this electron at different positions. And this is just, how many dimensions is this? Just one dimension, it's just x. So we're just talking about being on a line, going back and forth. So what's the potential energy of that electron on that line? I'm seriously talking about a number line, right? What's x? What's its potential energy on that number line? Okay, is it 12? Is it 8? How does the potential energy change on that number line? It could be, maybe it's like going up a hill or something. I don't know. But it depends on what's around it, right? If it's a bond, you have nuclei around it, and you know, it's changing as it moves in different positions. E is the energy of that electron. Okay. And you're only going to get certain possible energies with this wave function, as long as the wave function is right. Okay? You only get certain possible energies. And there's right and wrong wave functions. We'll talk about that down here in those plots. But notice how the wave function is, you take the second derivative, here's the second derivative, right, of the wave function, find out what it is, take the potential energy function times the wave function, figure out what all that stuff is, then you solve it. Here's your answer. You get a number. And then you get the wave function back again. That's just how it works. So you take the second derivative of your wave function, add it to the potential energy times the wave function, right? So you're taking the second derivative of a mess there, but it works. Okay. Yes?
Second derivative with respect to what?
X. With respect to x. Now, if you make it 3 dimensions, you don't have d2 dx squared anymore. You have, well, yeah, you have d2 dx squared, but you also have the second derivative with respect to y, with respect to z in 3 dimensions. So instead of writing all that, we call it del. Del stands for, well, del squared stands for d2 dx squared plus d2 dy squared plus dz squared, d2 dz squared. That means now our potential energy function has to be 3 dimensions too. Our wave function has to be in 3 dimensions, in x, y, and a z. But it's the same format. You take the second derivative of the wave function, throw in your potential energy function. If everything works, you get the energy, a number, and your wave function back again. Okay. Now the computer is going to be guessing at some wave functions, but it doesn't even mess with certain wave functions that are going to give certain plots. It's not going to use any wave functions that end up plotting like this, where you have in the first one there's a discontinuity, right? That it's 2 different values at the same point, right? Or it's not smooth in B, right? In C, again, you have this same different values at the same x point. Or in the last one, it just blows up on you. So those wave functions won't work. Okay. We said that there's no meaning to the wave function. But there is meaning to this. Usually when we said, what do these lines usually mean? Absolute value. Okay. That's not what they mean here. That's not what they mean here. It's called magnitude. That's what I say it. But what we're supposed to call it is probability. Oh, density. That should be an N. Probability density. Okay. Before we said there's no meaning to the wave function, but there is meaning to the wave function if you multiply it by itself. But it's a kind of a special multiplication. That's why they have this bar in here in the squared. Is that you can write probability density and write it this way, bar with the squared, but it really means the second one. And the second one is the one that really, really helps me because it tells you what to do, how to multiply them. You multiply the wave function times itself, but the little star means something. The little star means complex. Is this in the reading? Conjugate. For example, let's pretend psi is e to the I kx. What was I from the concept preview, Alice? What was little I? Square root of -1, right? It's imaginary numbers. If psi is e to the I kx, psi star is, to get psi star, wherever you see an I, replace it with -I. That's all psi star is. So psi star would be e to the -I kx. Okay. So probability density, which is, for example, in this box here, what's the probability of that electron hanging out in a certain region in space? We can kind of, I don't know if it really adds meaning to the wave function, but it adds meaning to multiplying the wave function times itself, or one of them's complex conjugate. Okay, the probability density. I guess that's the Born interpretation of the wave function. Okay. And life is easier. Is that what's coming up? No, there, it's down there. But notice they have a little r here. They already got rid of the x and the y and the z because they're in. Oh no, x, y, and z are still there. Okay. So let's just we'll leave it as that. We'll leave it as that. But does anyone know where it's heading? And I don't remember if you had this. I don't remember if you had this. You can use, to describe a point in space, you can say x, y, z. Or you could say what? You could say r, theta, and phi, right? You can say the distance out, right? That's your radius. And then what is this angle, right? And then what is this angle going to be, right? Combine those 3 points and r, theta, and phi. And it's kind of combining all those in that one plot. So it's got an r, it's got an x, y, and a z. Okay. But that's the idea. And that's kind of where we're heading. So how is this stuff useful? Okay. So if you, now for these wave functions, see how they have, this green one is the wave function. And you're going to see a lot of wave functions because you're kind of stuck. I mean, what functions do we know of can you take the second derivative of and get the function back again? E is one, right? So we're going to see wave functions with little e in it a lot. What's something else? There's only one other thing that I can think of. Well, 2, I guess. Well, no, well, not e. Well, yeah, I guess it would be. It's a little off. You'll see where I'm coming from. Something else. What can you take the second derivative of and you get it back again? No, because log, it's 1 over, you're screwed. You're not going to get it back. What's that? Cosine. Take the derivative of cosine, you get negative sine. Take the derivative of sine, you get cosine. But see that negative sign is there? That's what I was thinking. It doesn't quite work. Sine works even better, right? But you're still going to have that negative sign in there. But that's okay, because that's a number, right? They want the number out front. So you could just make your wave function be negative cosine or negative sine, and then if you're worried about the negative sign. So sine and cosine both work. You're going to see a lot of sines, and you're going to see a lot of exponentials for your wave functions. Now, if you plot those out, especially sine and cosine, all right, what does a plot of a sine look like? Sine of who knows what. Doesn't really matter. The sine function or the cosine function. What do these guys look like? Yeah, they're just like, yeah, just like that green guy, right? Okay. However, the green guy is smoothing out here and here. The reason why he's smoothing out is because of that potential energy function. There's a wall here. And that, because part of that wave function, right, here's where the potential, V of x, is infinity. It's a wall. That potential energy, it's such a high potential energy, the electron can't budge into it. Okay? It's like infinitely high hill. Baseball can't get up there, right? So that's why it's kind of dying out here and dying out over there. So if you take the wave function, now that's supposed to be my psi, and if you take psi star psi, in other words, or just multiply that wave function, multiply this thing times, I can't. How do you reproduce the exact same thing twice? I should copy and paste it. Yeah. Or I can just be really careful, maybe. I'm trying to draw the same thing twice there. All right? Multiply these guys together. All that happens is that the peaks get a lot sharper, right? But the negative times the negative is a positive. So there isn't any negative stuff anymore. Everything is just becomes sharper and goes up to the top. So it would look like, how many bumps do I have here? I have 1, 2, 3, 4. So I'm going to have 4 bumps. 1, 2, 3, 4. Right? Something like that is what it would look like. And that's what they're trying to do here. They have their wave function in the green plot, and then their psi star psi right below it. Okay? And again, it doesn't, and that's why that guy, yeah, the negative guy popped up. But again, it's dying on the ends because of that potential energy function. Remember, that's part of your wave function, this guy. So that's why he's dying on the ends, because you can't exist there. So when you look at this probability density, now there's physical meaning to this. You just look at this dark plot, right, the red one. Look at the psi star psi plot. It tells you where the electron is and its probability. It's just the area under the curve. It's got to be there somewhere. So there's a 100% chance of it being there. But there's what percent chance of it being in the right-hand side of the box? 50%. And that's half the area. You know, what is the probability of that particle, sorry, the electron being found exactly in the middle? What's the probability of finding that electron exactly in the middle? 0. You're never, ever going to find it in the middle. 0% probability. What doesn't make any sense? Right? Look at this ball rolling between this side and this side of the table. What are the odds of finding it in the middle? Just as good as anywhere else. Not even close. Look at that. You pick two different little areas, right? Like between 1/6 of the box and 1/7 of the box, right? That probability is different than, I don't know, 7/8 and, right? Just pick different little sections, little slivers of it. It changes. So it has equal, and it's very, very odd. But it works. It really works. This is what they find. They find this very odd behavior in the microscopic world. Okay? It's just how nature is. That is nature. Now, there's a couple of ways to look at it. One way is, oh, this is super complex. The other way is, thank goodness. Since we're in a Catholic school, thank God. Why? This means at the microscopic level, are things determined? At the microscopic level, scientists are saying what? That things are determined? No.
They can't be in the middle.
Yeah, there's some things that are impossible. You're right. That's a good point. There's some things that are impossible. But there's bloody choices in here. You have no idea, right? So in this one weird mathematical plot, to me there's a lot of philosophy. And that, heck, in the microscopic world, the stuff we're made of, there's probability. There's free will, whatever you want to call it, right? That's kind of strong to put it as an electron, but... Okay.
Does that go together with the idea that you can't find an electron at a certain position because it's always changing?
Maybe not so much because it's always changing. I think...
You can only identify where it might have been.
When you do an experiment, what this literally means is that such a percent of the time you'll find the particle here or you'll find it there. This is just position. We're not talking about energy now. We're just talking about position. So you probably find it here or there. And how I conceptualize this is the electron is acting not like a particle, it's acting like a wave. And then you have the standing wave idea. It'd be really nice in general physics if we did more wave labs. It'd really help you out here, especially in the tube. There's a lab in general physics, I don't know if you did it, but you have a water in this glass tube. And you take a tuning fork, dang, right, up on top. And then you slowly bring up the water. What happens? Now, the sound coming from the tuning fork is a wave, right? And it's a tuning fork, so it's one frequency. Nice sine wave you got going there, right? And it builds up standing waves. But it's only going to work if the guy matches, the distance is right. Then you get loud part, soft, loud, nodes, right? Nodes and big parts and nodes. Oh yeah? Is there a node in this plot? How many nodes? Nodes are where nothing happens. No sound. Yeah, there's one here, but there's also... there's actually 3 nodes. There's actually 3 nodes. That's this idea of nodes, standing waves. Electrons is acting like a standing wave. Okay. So to answer Adriana's question, that it's not because it's always changing. I think because standing waves. That's kind of what's going on. It's this darn wall that's causing it all. They call it the boundary conditions. This is what causes all this. Because if it wasn't for this wall, right, wouldn't it just keep going, wave would go on forever and ever and ever. So it's the boundary conditions that really causes quantization of energy. That really causes, the particle will be here, here, here. Or what's the probability of it being there, there? It's the boundary conditions that really cause it all. Okay. And that's the potential energy function. Okay. So we want to be able to say that what's the probability, call this a box, this whole thing's a box. What's the probability of that electron being in that box? 100%. You want to assign that number as 100%. To do that, you have to normalize your wave functions. Otherwise, in this problem, the 100% might actually be 212. That means 100%. You want to normalize everything to 100%. Then my 100% means the same as your 100%, right? It's just, that's called normalizing. Okay. So how do we normalize a wave function? If you want to say that the 50% chance of the box being in one side or the other, it doesn't make sense unless the wave function is normalized. Otherwise, you're not getting the right answers for 50%. So how do you normalize a wave function? You put a little n in there. So the normalized wave function has this symbol. The unnormalized wave function has symbol phi. Right? That little phi guy. So you take... the whole problem is really to find out what n is. Find out what that n is, multiply it by your unnormalized wave function, and you're done. You got it. Okay. So find n by setting the integral psi star psi d tau equal to 1. What's d tau? All 3 of the dx, dy, dz. If it's just a one-dimensional wave function, it'd just be dx. But this way it takes care of them all. Psi star psi d tau, set it equal to 1. Solve for that symbol n, and you'll have it. Okay. Well, it would look like n phi star n phi dx dy dz. Right. I guess you should have 3 integrals here if you want to do this right. And then, well, let's just stick to x. Life is so much easier, right? So what is the length of this thing? Let's call it 0. The box has a length of, I don't know, L. A lot of times they do that, capital L. So x goes from 0 to L. It can't exist outside the box because, I mean, it's infinity out there. So you'd only integrate, well, really you integrate from negative infinity to positive infinity, but a lot of it doesn't mean anything. If that's your box, you'd really just integrate from what to what. It's the only part that makes sense because it's 0 outside of it. From 0 to L. You can pull out the n squared if you want, right? Phi star, phi. This is what it's going to start looking like. I need to just keep doing the math, all that concept preview stuff. Because I bet you that they're going to have sine squared in there. That's why we're messing with all this, and exponentials. Okay, that's why we had all those trig functions. Now our life will also be easier if we stick to spherical polar coordinates. So there's going to be, the integrals are easier. A lot of life is just simply easier. So that's why you'll see a lot of, you may not see very much x, y, and z later on in the homework as they get more complicated. Okay. Now if you do that, d tau we said was dx, dy, dz. But if you jump into spherical polar coordinates, look what d tau then becomes. R squared dr sine theta d theta d phi. So it's, your d tau is a little bit uglier in spherical polar coordinates. But we'll live with it. So remember when you're doing, that would be a triple integral. Everything with r you put in front of the dr. Everything with a theta you put with the sine theta in front of the d theta. And everything with the phi you move into there. All those integrals are multiplied by each other. It's like in our concept preview. Okay. Oh, and our limits. I don't have those written down. For r, it goes from 0 all the way out to infinity. Theta goes from 0 to pi. And phi goes from 0 to 2 pi. So those would be the limits on our integrals. Okay. Let's see. Page 298. I had a question there. Okay. Is that part of the... Oh, it is. Oh, it's a self-test. We can go ahead and do it. Hopefully it's typed up. I thought maybe you had to do it on our own, but it's here. This is what I was looking at. Self-test, 11.4. Oh, it does say C book.
Yeah.
Okay, self-test, 11.4. Let's check that out. If you don't have your book, that's fine. I'll write down the question. So I'm on page 298. And normalize the wave function given in self-test 11.4. Which says normalize the wave function given in self-test 11.3. What is that? Okay, I have e to the negative 2r over a naught. That's my phi. E to the negative, what did I say? 2r over a naught. We're supposed to normalize it, right? Okay, so what was the trick? The trick was normalize it. That has to equal 1. So what does that mean? That means psi star psi. Right? That's what it means. It has to equal 1. Oh, I forgot my d tau. Okay, because that magnitude of the wave function squared idea is psi star psi. Okay. Oh, I should get my book here. Do they give us anything else? No little details? Okay. So let's put in our wave function here. Our wave function is going to be what times phi? That big N, right? Our normalization constant. So that means our wave function is really n times e to the negative 2r over a naught. So let's put that in. We want 1 to equal the integral psi star psi. Now, is there a little I to worry about? There isn't. But if there was, we would replace it with negative I because it's psi stars first. But it's not there. So there's no little I, so we just put it in. N e to the negative 2r over a naught times psi, well, same thing again, n e to the negative 2r over a naught I'm not going to skip anything. Okay. What's my d tau? All I have is an r. Yeah, we have to, even though there's no, in our wave function, if they want us to go over 3 dimensions, this is, you just kind of have to, you learn from practice, I guess. They want it to be 3 dimensions. That's what the d tau means. So even though there's no theta or phi in here, all there is r, that doesn't change this. You still, the whole gambit. What do we say? R squared sine theta, right? So we can combine the ends. So before I write the d tau part, e to the negative 2r over a naught times e to the negative 2r over a naught, that's what? Well, how do you multiply exponentials? Yeah, you add them up. So it'll really be e to the negative 4r over a naught, right? D tau. Now my d tau is, we wrote it up here somewhere. Here it is. That's my d tau. R squared dr sine theta d theta d phi. Okay. Well, we should probably add in our other integrals then. Our r, he goes from 0 to infinity. Now I'm writing the r one first because that's the innermost, right? dr is first, so that's why I'm writing him first. The next one is theta. And theta goes from 0 to pi. And then the last one, 0 to 2 pi. Okay, so let's clean this up a little bit. Let's put these 3 integrals like we're used to doing it. One has to equal this whole ugly mess. Can we pull the n squared out of all 3 of these integrals? Yeah, it's just a number. We're going to find it just to be a number. So let's pull it all the way out. Right? And then we can bring the d phi stuff all together. Right? Remember, that's how we did it. We had triple integrals. We just multiplied the individual integrals together, and it's 3 components. So we have 0 to pi of our, wasn't that 0 to 2 pi, wasn't it? And bring all the d phi stuff together. Is there anything to stick in there? Yeah, just d phi. So we're done with him already. Take that times the integral, 0 to pi. All of my theta stuff. I forgot a d theta in here, didn't I? All we have is a sine theta, right? So sine theta d theta. And then we have 0 to infinity. All my r stuff. R squared e to the negative 4r a naught dr. Okay. So we're about out of time. So what I'd like you to do is finish this, and then we'll work on the. So this is a you do, and then we'll work on homework next class period, right?
So we just do the self-test?
Yeah.
Homework?
So you just need to do. Well, heck, you could pretty much do the homework, couldn't you?
It's not yet such a problem.
It's the same question, pretty much.
Normalize.
Yeah.
Part B.
I think you'll be okay, right?
We'll try.
Try, give it a shot. So that means do the bold words for 11.5 and 11.6. Watch the concept preview for this stuff. It'll help you out.